Thank you. I'm Toi Tomita from YNU in Japan. I talk about efficient and tightly secure identity-based encryption scheme from RLWE. This is a joint work with Junji Skata from YNU Japan. Okay. First, I talk about the background on our works. So IBE is identity-based encryption, for short. IBE is extension of public key encryption. Any strings like email address can be used as public key encryption. So in IBE, the first authority generates master public key and master secret keys. The full encryption Alice can be used Bob's email address as Bob's public key encryption, public key. Then Bob receives from authority his secret key. So next, I talk about security of IBE. So the security definition of IBE definition as game between adversary and simulators. First, the simulator generates a master public key and master secret key and gives master public key to the adversary. So during the game, the adversary can adaptively make secret random oracle queries and secret key queries. At some point, the adversary sent a message and a challenge identity, ID star. Then the simulator generates, the simulator returns honestly generated ciphertext or randomly sampled ciphertext. Finally, the adversary outputs guess B prime. Then the success probability of the adversary's guess is negligible. We say that IBE scheme is adaptively anonymous security. We also consider tightness of the security proofs. So the security of the cryptographic schemes based on the hardness of some computational problem P. Then the advantage of the adversary in breaking the security of scheme pi is almost the same. The algorithm advantage of in solving the computational hard problem, we say that the proof is tight. Do not show. This table shows a comparison of previous works in lattice-based IB scheme in the random oracle model. We focus on two schemes, DLP48 and KYY18. Does not display. And for the efficiency, the DLP14 achieved compact parameters other ones, rather than. But the security proof is not tight. For the tightness, KYY80 achieved tight security, but the scheme has larger parameters than DLP48. So we consider the following problem. Can we construct efficient and tightly secure IB scheme from standard lattice assumptions? Sorry. We have affirmatively answered this problem. We propose new efficient and tightly secure IB scheme from RLWE assumptions. So our scheme has compact parameters are the same as DLP ones. And our scheme achieved tight security. So, this is our result. Our contribution is efficient and tightly secure IB scheme from ring RLWE assumptions. So our approach is simple. Our scheme is obtained by instantiating a GPV IB scheme by compact approximate trapdoor samplings. Then our security proof is obtained by combining K-wise tight security proof with RLWE with hints. I recall the GPV IB schemes. In the GPV IB scheme, master public key is a random matrix A, and master secret key is a trapdoor for it. And secret key for ID is a short vector GID that's satisfying these equations. Then a ciphertext of ID for ID is a dual relief encryption for matrix and vector UID. And finally, decryption can be done by computing the inner product between ciphertext and secret key. So we also record K-wise tight proof or overview. So in their proofs, the main idea is the simulator samples GID and programs H of ID equal to A times GID for all identities. So this allows the simulator can answer all secret key queries, and the simulator can generate the challenge ciphertext for all identities. Then simulator behaves identically for all identities. Then, since the simulator never aborts the security proof is tight. So we review how to simulate the challenge ciphertext in their proof. Or the challenge ciphertext is simulated by using secret key for ID start, that is ZID start. In this case, the distribution of E prime and in the original ciphertext and EGID start in the simulated ciphertext are different. Then they adjusted by the noisily randomization techniques of KY16. Then we use RLWE to randomize the C0. And finally, we randomize C1 by using regularity lemma using entropy of GID stars. So finally, the ciphertext is completely random, then no information on M and ID star. So we consider also efficiency of GPVIB schemes. So that is trapdoor sampling techniques. So in the by using trapdoor sampling, we can efficiently find a short vector G by using the trapdoor. That's satisfying these equations. But to use the trapdoor sampling, it is necessary to set M equal to order n log Q, so large. This leads a large matrix A. Then we have a large master public key and SKI ID and the ciphertext. To avoid this, we use a compact approximate trapdoor by proposed recently YJW23. So by using approximate trapdoor, we can efficiently find a short vector Z even for that satisfying these equations, even for smaller M go to order n, where G tilde is the approximate error. Then this leaves smaller master public key and secret key and ciphertext. So this is our scheme, and these orange boxes are the differences from GPV-IBE. The main difference is master secret key is approximate trapdoor and the secret key is approximate pre-image C. So we tried to tight proof by KYY18 for our schemes. So first, we simulate the samples GID, G tilde ID, and programs HID equals to A times GID minus tilde GID tilde for all IDs. Then the simulator can answer all secret key queries, but the simulator simulates the service ciphertext. So as in KYY18, we try to simulate the ciphertext in C1 by using secret key of G for ID star. That is GID star. So in this case, where we obtain the following equations. So unfortunately, this additional error terms SGID star due to the approximate error, it cannot be adjusted by noise randomization techniques by KY16. The noise randomization can adjust the error appearing before the evaluation of A times GID star, but cannot adjust the error appearing after the evaluation of GID star. To solve this problem, we simulate the challenge ciphertext using GID star and additional error terms S times GID star tilde plus EGID star. So we will write C1 as follows. So this is exactly same distribution, original ciphertext and simulated ciphertext. But S is LW secret and E is LW errors. Then the simulator cannot obtain that values by to re-randomize C of 0. So to solve this, we introduce the LW with hints. LW with hint ensures that LWE is hard even given some hint of LW secret and LW errors. In this case, the hint is S times G tilde ID star and plus E times GID star. Fortunately, the hardness of LWE with many hints is almost same the hardness of LWE. So then we use this. We simulate the challenge ciphertext by using LW with hint. So by using LW with hint, we can randomize the C0. Then by using Gaussian regularity lemma, we can randomize also C1. So sorry, I got conclusions. Our contribution is an efficient, tightly secure IB scheme from ring LW assumptions. The approach is simple, and our scheme is obtained by instantiating GPV IB with compact approximate trapdoors. The proof is a combination of KYY's tight proof plus LW with hint. Then our proof is somewhat generic since it applies to any approximate trapdoors. the feature works as follows. Thank you for listening.
Thank you. Any questions or comments?
Thank you for the talk, and I want to thank you for dealing gracefully with the technological issues we had here. No, it's a difficult situation when the information you need to present is not visible. I wanted to ask, it was a few slides back, I think maybe slide 16, maybe? Yep. Yes, this LW with hints here, these results, I don't remember these explicitly. But I have a naive question about this. Is this related to the same type of analysis as like key robustness for LWE? Yeah. If you have skewed your distributions you're sampling from, that you can reduce it, like it self-reduces to another instance where you have many samples instead of just one. Is it that sort of result? Sorry. It's difficult to explain maybe my question, but let me try to be clear. There's a notion of key robustness for LWE, where if you're sampling from a skewed distribution, that the problem reduces to itself, where essentially the number of samples you get gets multiplied by some factor that takes care of the skewness of this distribution. And I'm wondering if that's the same type of result as these papers, or if you know.
Oh. I don't know. Sorry.
Yeah, I'm probably just being too cryptic. Yeah. Okay. Thank you.
Any further comments? Yes.
Yeah, my question is a bit related to the one that you just asked, which is that this LWE with hints, it sounds a lot like the hint MLWE assumption that was put forward in Crypto 2023. Where you have a hint, the same shape as the one in orange in your slide, but it's that plus some randomness that the adversary doesn't learn the randomness. And so I was wondering if that's related, the two of them. I was wondering if this is related to the hint MLW assumption from Crypto 2023.
Maybe some relation is there is some relation, but we use maybe another type LW with hint introduced by MKMS in 2023.
All right, thank you.
Oh, sorry.
All right. So we're running a quick one. We're a little bit behind schedule.
Thank you for the talk. I just wondered, the last step of the proof is to use some regularity argument on C0 times CID star, I think. Yeah. And what kind of impact this regularity argument has on your parameter sizes and stuff like that? Yeah.
Gaussian regularity in the ring setting, we can use more compact size.
Mm-hmm.
So then we use Gaussian regularity in the ring setting.
Okay. And so you, as such, require like a larger Gaussian parameters, I guess?
Yeah. Huh?
You require larger Gaussian parameters?
Yeah, maybe. Slightly larger.
Yeah, you trade off the dimension for
Yes.
larger. Okay, thank you.
Yeah, thank the speaker again. Thank you very much.